This new unit is Unit 11, and it's titled Solutions. We've already worked with solutions. Solutions are when you have something, usually in chemistry, we have a salt dissolved in another, or in a liquid, usually that liquid is water. Anytime you have something dissolved in something else, you have a solution. And we started that last lab last week. You guys made solutions, right? You got a little beaker, put a little salt in them, put some water in it, dissolved it. You made a solution. That's what a solution is. Our first section here. Today we're working with concentrations, which we're going to have a couple different ways that we measure concentrations. And we'll go over those today. The basic term, though, the concentration, a couple of key terms there. But ultimately, the idea of a concentration is that we're looking at how much solute, and that's going to be your dissolved particle, is in your solvent. Again, I'm going to use the term salt a lot. In regular, plain old American English, when we refer to salt, I know a lot of times we're just talking about what you put in your french fries, sodium chloride, which is definitely a salt, both in what you eat and in chemistry. But in chemistry, there are a lot of different salts. We generally use the word salt to apply to just about anything that's an ionic compound we call a salt. So you guys will hear me say salt a lot, and it doesn't just mean table salt. It's not always just what you put on your french fries. So for example, when you guys made that solution last week, when we did that lab, you guys had two different salts. You remember that? You put those two white substances into the beakers. They were both salts. Now, neither one of them you'd want to put on your french fry, but they were both, in the chemistry terms, salts. Generally, your salt is your solute. It gets dissolved by your solvent, which again is almost always going to be water. Kind of an important concept here. Your solvent and your solute together makes your solution. Those two things together make your solution. And just so we're good with the terminology we'll be using, got a quick image here. Calling this our beaker. We've got some water in it. And then we've got these little particles that are dissolved in the water. So the water is the solvent, and it usually will be water, though technically the solvent is whatever there is more of. So if I had a big gigantic beaker full of salt and I dropped a droplet of water in there, then technically your solvent would be the salt and your water would be getting dissolved. So that's kind of weird. We don't really have that situation very often. So usually your water is your solvent and your salt is your solute. Now I know I've got these dots drawn large enough that you can actually see them. And that's almost never going to be the case. Again, you guys made those solutions last week. Remember, after you stirred them for a minute or so, you didn't see anything left. They just looked like crystal clear water. So you usually can't see anything in a solvent. But we've got them drawn there just for our diagram. So one more very similar diagram here. And just so that we're comfortable with terms, you guys will see these terms from time to time. Dilute means that you have a low concentration, not very much solute per solvent. You guys hear the term dilute from time to time, and we also have concentrated. Which means a high concentration. Lots of dots, lots of solute per solvent. And you guys will hear these terms pretty often, so just so that you are familiar with them. Dilute means there's not very much salt in there. Concentrated means there is. There's a ton of salt in there. Now, as you might have guessed, chemistry, we don't particularly like to just use qualitative terms. Right? Who cares if it's dilute versus concentrated? We want quantitative terms. We want numbers. We want to know exactly how concentrated that is. So we don't very often use dilute and concentrated when we're figuring things out. We want to know exactly how much salt is in there. And we have a couple of different ways to do that. First way, off the page, I'm sorry. Thank you. First way is percent volume to volume. This will be milliliters to milliliters. We generally use this for two liquids. In fact, I bet you guys have seen this before in your lifetime. Every time you go to the grocery store, when you see percentages listed, this is what you guys are seeing. Ever buy 2% whole milk? Guess what that percentage is telling you. This is one you guys don't have to worry about for another, how old are you guys, 15 or 16? This is one you guys don't have to worry about for another 5 or 6 years. You see this a ton, though, when you're an adult. Proof. It's something, for whatever reason, it's something the alcohol industry uses a ton of. So they mix alcohol with water. they come up with a percentage, and then I think they just want it to sound bigger, like you're getting more alcohol. I don't know why. I have no idea. But proof is 2 times the percent volume. Just double the percent volume. Again, my only guess is they want to make you think you're getting more alcohol, so they double it and call it proof. No idea why. To find your percent volume to volume, not a whole lot to it. You just take your milliliters of solute, and this is important, divide it by your milliliters of solvent, times that by 100%. This is important though. Oh, excuse me, strike that. Hang on. There I go, messing it up again. Did this first period too. I even made a note to myself not to do it again. This is important, and what I said the first time is dead wrong. It is solute per solution. Solute per solution, not solute per solvent. So keep in mind what we looked at up here. The solution is your solvent and your solute together. It's both of them added together. So make sure you have that on the bottom. I'll do an example here in a second. You guys get to see that illustrated. But watch out for that. Ignore what I said the first time. It's not solvent, it's solution. All right, so here's the type of question from this unit. Guys, very important you start this off the right way. And a lot of you won't want to, and some of you won't. And I'm going to take off points because I'm telling you to start off this way. That's number one. I'm going to take off points. But number two, guys, if you're not doing it the right way, starting now, I know you might be looking at it, I can do that. No problem. You probably can. I can disagree with you. It's not a problem of doing it the right way, though, or being able to do it. It's a problem of doing it the right way because it will get harder. And if you don't build the habits now of setting it up the right way, you're going to struggle when it gets harder. So slow it down, do it the right way, which is what I'm about to show you. Or again, A, I'm going to take off points, and B, more importantly, you're digging yourself a grave. You are not going to be able to solve these problems when they get more complicated because you will not have built up those skills. So here are the skills I need you to practice with right now, even when it's easy. We're looking for the percent volume. That means milliliters of solute over milliliters of solution. So question mark, milliliters of solute over milliliters of solution. You just put SLN for solution. There. I know what I'm looking for. I've got it set up. This is an important skill to develop. Very important skill for you guys to develop. Is equal to, well, what do I have? I have 45 milliliters of ethanol. You guys know what ethanol is. We did organic chemistry already. F means 2. The OL means it's an alcohol. Yeah, we know that. That's terribly important for this problem, but you guys know what that is. 45 milliliters of ethanol. Just symbolize the ET for F and the OL for the alcohol. Divided by, then they also gave us 125 milliliters of solution. Cool. We got our bottom number 2. They gave us everything we need. Yeah, that was pretty easy. Yeah, I'm sure almost every single one of you guys could have done it without this right here. But again, you want to practice that now while it's fairly simple so you get really good at it when it gets more challenging. Put that down, then we got this, and the final thing here, we got to multiply it by 100%, and now we're ready to calculate. We got everything we want, everything we need. 45 divided by 125 times 100%. Double check for sig figs. We've got 2 here. We've got 3 there. It's a multiplication division problem. So we're limited to total number. Doesn't matter how far past the decimal. Total number is 2. So 36 will do. 36% volume to volume. Not too shabby, huh? Hey, let's tie on. Sometimes we'll do this. Let's tie on a little stinger here. And for whatever reason, I have no idea, but for whatever reason, we measure alcohol in proof. But that's really simple. What's that? Yep. 2 times our 36%. All right, I need my calculator for that. $72 proof. And why do we do that? Probably because people are silly and see the 72 and think they're getting more than what they would be with 36, even though they're the exact same. Silly people.
Alcohol, it'll be like 36% alcohol in it, and then the rest can be like anything.
Well, it's usually water. Yeah, it's usually water. Yep.
And that's just with alcohol?
It's very common with alcohol. Alcohol is a really good example of 2 liquids, water and ethanol. So yeah, really, really good example. You see it all over the place. It's hard to walk through a grocery store without seeing a percentage listed, or, as alcohol likes to think they're tricking people, a proof listed. Another common one, and you see this all the time in grocery stores. Oh, hang on. One more example. I wanted to show you guys the trick here. On the page. So here's an example of how these 2 problems are different. Boy, they look really similar out the gate, don't they? We've got our 45 milliliters of ethanol, and we got our 125 milliliters. The big difference, and you guys are going to have to catch this, I'm pretty sure it happens at least once in your homework. The big difference is that this is 125 milliliters of water. On that first example we did, it was 125 milliliters of solution. Remember, the solution is solvent and solute. Well, water isn't the solution. Water is the solvent. It's the other part of the solution. They didn't give us the solution this time. We're going to figure it out on our own. Luckily, I imagine we're all smart enough to do that. Again, let's start it off the same way. We're looking for milliliters of solute over milliliters of, and that's key, solution. Solution, SLN for solution. Okay, I've still got my 45 milliliters of ethanol. That hasn't changed, so put that up top here. That's my milliliters of solute. That's dissolved in 125 milliliters of water. Now the problem is that's not my solution. My solution is both of them together. My solution is solute and solvent together. So that's kind of the trick to that one. Enter into the calculator all in one step. 45 divided by, I need to use my parenthesis symbol there. 45 divided by parentheses, 45 plus 125, close parentheses, times 100%. Just two significant figures here. This is an addition step. So we're actually going to end with three significant figures. But because we started with only two, we're limited to just two in our final answer. So we're just going to call this 26%. 26%. Do you guys feel comfortable with proof? Not terribly comfortable. We don't need to do another what is the proof, right? You guys get that. Cool. Awesome. All right, so we see this difference then between 125 milliliters of water versus in that first problem is 125 milliliters of solution. Okay, excellent. All right, our next type of concentration, again, you'll see this a lot, grocery stores, regular, every day, you see this a lot. Mass to volume, which is measured in grams per milliliters. Usually have this when you have a solid. Dissolved in a liquid. And very similar to the other one. You find that percentage by taking your grams of solute, dividing by your volume of solution, and multiplying by 100%. All right, for next example, let's knock it up a notch. I'm guessing if I gave you guys grams of a salt and a volume, you could figure out the percentage. So let's take it up a step. Let's do a slightly more complicated example. Got too low again.
That's 200% or
2%, 2.00. All right, this is a type of problem that usually gives my students fits. They see this, they don't see what they're directly asking for. It doesn't say what is the fill in the blank. It says describe the preparation of. So you got to kind of figure out what the question's asking for. A lot of times this gives people fits. Okay, let's take a look at what we have. We have a percentage. Now we're going to have to get used to seeing that. That percentage is kind of like a double unit. That is 2.00 grams per 100 milliliters. That's what a percentage is, right? 2 out of 100, that's 2%. If we're doing a mass to volume, that means it's grams to milliliters. So we got a double unit there. That's what that percentage tells us. And we have a volume up here. There's a volume for us. So what exactly are we missing? What are they asking for us to solve for? What do we not have?
You don't have the solution.
What about the solution?
It's in the chemical equation. What do you have to do?
Well, we have the concentration of the solution, and we have the volume of the solution. We got to solve for something, but you guys are going to have to figure out what we need to solve for. Anybody home? You guys are seeing what we need to solve for?
Glucose?
What about the glucose? What part of the glucose, though?
The mass volume, right?
Excellent. Yes. What we're going to need to solve for is the mass of glucose. You're being asked to make 2.5 liters. Okay, you can do that. We can all go measure 2.5 liters. Here's the concentration. What this question is asking is what mass of sugar, that's glucose, what mass of glucose do we need to put into the water? What do we need to dissolve? So this question is kind of double question. We got to first figure out what they're asking for. And then second of all, now we got to solve it. So yes, absolutely. This question is asking for what mass of glucose? What mass of sugar do we need?
So the C is that.
That's C6H12O6. All right. So we have our options here. Last chapter, it was kind of easy. We always just put down the number that they gave us. Well, this time they gave us two numbers. Which one do we choose? My advice, whenever possible, choose the number that only has a single unit. This one has a double unit. Don't start with it. This one, only a single unit, liters. That's the one we want to start with.
Wait, how do you know? Like
Well, this one has 2 liters, two units, excuse me, right? Grams and milliliters. See the 2 units? If you can help it, don't start with that. This one just has the 1 unit, liters.
oh.
All right, so we've got 2.5 liters. But guess what? We don't want liters. We want milliliters. We want milliliters. First thing we got to do is we got to convert this into milliliters. Hopefully we all remember some of our basic conversions from first semester. There are 1,000 milliliters and 1 liter. Now that we've got liters, cross that out. Now that we've got, milliliters, Now we can use our 2%. Our 2% allows us to convert from milliliters into grams. We just got to make sure we get our units lined up correctly. We want milliliters on the bottom. So there's our milliliters on the bottom and 2 grams on top. How do we know it was grams? Well, we're looking for a mass to volume percentage, grams per milliliter. How do we know it was 2? Well, it told us 2%. 2 out of 100 is 2%. And guess what? We got our answer, grams. Grams. Cool. We can solve. .5 times 1,000 times 2. Whoops. Almost forgot something. You guys notice what it was? Yep, I almost forgot to divide by 100. In fact, I did forget. I caught myself right at the end. Yep, almost forgot to divide by 100. I got my 5,000 and divide that by 100 because it's 2 grams per 100 milliliters. Forgot about that 100 in the bottom. There we go. We got a 50. 3 significant digits. This is infinite digits. These are an exact conversion. 3 significant digits. So our answer needs to have 3 significant digits, which means we're actually going to have to add them this time. Usually we're taking some off. This time we need to add them. Oops. Don't want to draw a box around it just yet. All right, we've done the math. We've got our numbers. The problem is we need to answer the question. Describe the preparation of. And this can kind of be a little bit of a trick as well. Here's the thing. If I go and I get 2.50 liters of water, you guys are all with me? You're picturing that? I'm holding on to exactly 2.50 liters of water. Measured it perfectly. What happens when I dump 50 grams of sugar into it? Yeah, my volume is going to go up. That sugar is going to raise the volume. I'm not going to have 2.5 liters anymore. I just wrecked everything. It's not like I can now remove water. I can't. My water has dissolved sugar in it. I just ruined my whole experiment doing that right there. So it's very important to word this correctly. Very important that we word it correctly. We want to add our water to our sugar. Before I even measure out 2.5 liters of water, I want to put my 50 grams of sugar into my beaker or my device, whatever it is I'm using to measure. I want to put my sugar in first and then add the water until I get a total of 2.5 liters. Because I'm not going to use 2.5 liters of water. Remember, the solution is both of them together. If I have just 2.5 liters of solvent, I'm going to have more than 2.5 liters of solution because my solute will knock it up a little bit. So, kind of getting the wording right is kind of the last little trick to that type of problem. You want to add the water to the sugar, not the other way around. Questions? All right, one more type of concentration, the chemist's favorite. what the chemists call molarity. It's a chemist's favorite. We find molarity. First of all, we symbolize it, big M. So you're going to see a lot of big M's this chapter and next chapter. A lot of big M's. We symbolize it, big M. We calculate it. Moles of solute over liters of solution. Now you guys can start to see why it's a chemist's favorite. Got the mole in there. Because we got the mole in there, guess what? We can go straight to stoichiometry with this. Oh, you guys look so excited. Now you see why it's a chemist's favorite. Yeah, when we get that mole, we can start to relate back to balanced chemical equations and masses and all those good stuff we worked with last chapter because of that mole. So that's why this one is the chemist's favorite. You'll see those percentages when you go to the grocery store. But in chemistry, we love molarity. So first example, what is the molarity of a solution that contains 0.90 grams sodium chloride dissolved in exactly 100 milliliters of water, or excuse me, of solution? Just like with the percentage, we have to see percentage as grams over milliliters. Well, this one here, we need to start seeing this as moles over liters. So anytime you guys see the big M or the word molarity, for units, think of moles over liters. Remember last chapter how I told you guys whenever you see grams per mole, that slash sign is just disgusting. Don't use it. It's impossible to use mathematically. Put grams over moles. Well, pretty much the same thing. Whenever you see the big M, don't use it. It's too difficult to use mathematically. It's a double unit. Whenever you see that big M or the word molarity, you guys should think moles over liters. Mathematically, this works a lot better. All right, so what is the molarity? Instead of writing question mark big M, question mark moles per liter. Mathematically, we can work with this. Big M, you really can't. Is equal to, well, they gave us two things. That's okay, we're looking for two things. I know I can go milliliters to liters. That part will be pretty easy. Milliliters to liters. So if I need to go milliliters to liters, that goes on the bottom. I can go milliliters to liters. That conversion I can make. And on the top, grams to moles. Hey, that's another fairly easy one. Maybe not as easy as that first one, but that's fairly easy. We spent all of last chapter doing that kind of conversion, grams to moles. We go grams to moles, and we go milliliters to liters. We are set up. You guys get to pick which one you want to do first. Easy or hard? What do you think? What do you prefer?
Hard.
Do the hard one first, get the hard one out of the way? Absolutely. And if, guys, if you prefer easy, go easy first. Doesn't matter which order you do these in. Hard, I'd say going grams to moles is the hard way. So let's start with that. Grams on the bottom, grams NaCl on the bottom, moles NaCl on top. This should look familiar. We've been doing this for 2 or 3 weeks now. What we need is a molar mass of NaCl. And we get that with the handy dandy periodic table. We add together 1 sodium. And 1 chlorine. Goes in the calculator. Our molar mass of sodium chloride is 58. 0.442468 grams per mole. Let's check our significant digits. Ultimately, it's probably not going to matter, but good practice to do. 1, 2, 3, 4, 5, 6 past the decimal. 1, 2, 3, only 4 past the decimal. Our value should only go 4 past the decimal, so I'm going to underline that 6/8. Those are not significant digits. And look at that. I've got a grams per mole. That's what I wanted right here, grams per mole. So just got to pick the number. (58.442468) grams of sodium chloride per mole of sodium chloride. My grams of sodium chloride is canceled out. I have moles on top, and look, that's what I wanted. The advantage of having set this up properly. That's what I needed. Now I need to do the other step where I go milliliters to liters. And I think this one's pretty easy. We should all have that memorized. There are 1,000 milliliters in 1 liter. And I need to get milliliters on the top because on the bottom here, now it's going to cancel out. I've got liters on the bottom, moles on top. Time to solve. 0.90 divided by 100 divided by 58.442468 times 1,000. Voila. Double check our significant digits. I started with only 2 right there. This said exactly 100 milliliters. So if it's exact, that means it's infinite significant digits. So we're going to be limited to just 2 significant digits. Our molarity is 0.15 molar NaCl. Guys, if you like using that moles per liters, I love seeing moles per liter. If you're comfortable writing the big M, go for it. That's what you'll see most often in chemistry. but I love seeing moles per liter. Mathematically, it works a whole lot better. It's the same thing. It's the same thing. You are welcome to write it either way, whichever way you're more comfortable with, I'm good with. Either one is a very acceptable answer. All right, one more example with you guys.
Thank you. I found some bunch when I walked in, but I'm under stress. I can't see it. Lab stress. I've run out of time.
All right, so one more type of example, something else you guys see in your homework this weekend. How many liters of solution hold 23.4 grams potassium chromate of a 6.0 molar potassium chromate solution? So they're telling us the concentration, they're telling us the grams. This time what they're asking for is what volume do you have? How much of this liquid do you have? Here's the concentration and here's the mass of solute. How much liquid do you have? How much, what's your total volume? All right, so question mark, we know what we're looking for. We are looking for liters solution. We'll start with that. Is equal to, well, again, they've given us two things to work with. What we need to be able to see is that big M is really moles per liter. That's a double unit. If you can help it, don't start with it. Yeah, that's a double unit, moles and liters. This one here is just a single unit. So let's start with that there. All right, 23.4 grams potassium chromate. Wow, just like last chapter, we have to go grams to usually about the only thing you can go with grams to moles. What do we need for that? But a molar mass. We need 2 potassium. One chromium, Cr. I won't be able to squeeze the rest in up here, so I'll come down here. And 4 oxygens. So now we're ready to calculate. Ooh, it's a big mass. Hey, again, I know they're probably almost certainly not going to be important, but good to get the practice in. Significant digits, we went 4 past the decimal, 4 past the decimal, 4 past the decimal. It's an addition problem. So it matters how many places past the decimal we go. And our answer only goes 4 past the decimal. How about that? 4, 4, 4, and 4. We're good. No underlining, no extra digits. We got the exact number of digits we need. Sweet. Doesn't happen very often, does it? There's our mass per mole. And then final step, again, we're looking for liters. Right now we have the moles. If you want to, you can cancel out that grams. Grams is gone. Last step, look at our concentration. Look at that molarity. That'll allow us to go from moles to liters. We just got to make sure we line it up properly. Moles is on top, which means I want moles on bottom. Moles per liter. It's the same exact thing. Moles per liter. So I just got to make sure I get the right number. It's 6 moles per liter. And look at that. Moles is canceled out. We have liters. That's exactly what we're looking for. Now it's just time to crunch the numbers. 23.4 divided by 194.1903. It's not times, divided by 6. There we go. Not a very big volume. Not surprising. This is a huge molar mass. We want it to be super concentrated. 6 is a high concentration. And we don't have very much salt. So our volume is going to be quite small. Only about 20 milliliters, which is not much. Why only 2 significant digits? Well, look at that 6.0. That's only 2 significant digits. So our volume for our very concentrated solution without much salt is pretty small, 0.020 liters. Questions?